All right, let's get started. So, let's see. First thing, homework. You got your homework done? You don't have to turn it in until the end of class, but don't forget about it. Anyways, so the first section that we're covering today, section 5, it's going to be our introduction to proof. So the next homework that's coming up, you're going to have a ton of proof problems. And that's how the majority of the class is going to be from here on out, just a bunch of proofs. So chapter 5, we're introducing you to proofs. We're going to have you do some simple proofs to get comfortable with it. And let's make sure that we remember the definitions that we're going to have to use over and over again, just to make sure that you don't forget them. So the first definition we talked about last time was divisible. What does it mean for A to divide B, or for B to be divisible by A?
There exists an integer such that B is equal to A times an integer. Right?
Yeah, perfect. So it means that I can find some integer C such that A times C is equal to B. For example, do we know that 2 divides 8? How do we know 2 divides 8? Because there's some integer, namely 4, such that 2 times 4 equals 8. That's how we know 2 divides 8, right?
Yeah.
Okay, now even. What did we mean by even? What's an even? I can't hear you.
It's divisible by 2.
It's divisible by 2. An integer A is even provided 2 divides it. It's divisible by 2. If 2 divides A is even. What's odd?
The number can be rewritten as like 2x plus 1.
Perfect. If A is odd, then that means there exists some integer x such that I can write A equals 2x plus 1. If I can express it this way, it's even. Notice if 2 divides A, that's the same thing as A is equal to 2x. If 2 divides A, that means 2 times something equals A. So if I can write it as 2x, it's even. If I can write it as 2x plus 1, it's odd.
Right.
Is 17 even or odd?
Odd.
Odd, because it's 2 times 8 plus 1. There's a plus 1 there. 16, on the other hand, is even because it's just 2 times 8.
Yeah.
So if I can express it this way, even. If I can express it this way, odd. Right? Perfect. Okay. Let's see. What other definitions do we have? Prime. What does it mean to be prime?
That it can only be divisible by 1 in itself.
Perfect. And?
It's greater than 1.
And it's greater than 1. Those are the 2 requirements. So P is prime provided P is greater than 1, and the only divisors of P are 1 divides P and P divides P. And that's it. Those are the only ways that we can divide P. Then it's prime. What's a composite?
It has a different number that can divide by it.
There is a number greater than 1 and less than the actual number that can be divisible by.
And it's also greater than 1. Yeah. So if A is, we'll use C for composite. If C is greater than 1, and if there exists A such that 1 is less than A is less than C, and A divides C, then it's composite. If I can find an integer between 1 and the number that divides it, and the number itself is greater than 1, then it is composite. Although we don't need the greater than 1 because this is already forcing it to be greater than 1, huh? So we can just say that. All right, was that all the definitions we had last time? I think so. It's all the ones we're going to use for what we're proving today, so as long as you understand those, and you can do all these proofs and don't really need me, but I'll walk you through them anyways. Okay, before we start doing proofs, let's go over what proof is. Now, we give you a very high-level intuition of what proof is in this class, because we're not building an axiomatic system. So in this class, what do we accept as a proof? It's an incontrovertible, a proof incontrovertibly shows a statement is true. Make sense?
Mhm.
There's no ambiguity, there's no wondering, there's no possibility of it being false. That's what we mean by you've shown it to be, or that's what we mean by you proved it. You've shown it to be true. There's no way to challenge it, there's no way to question it. Okay? Question. Can we prove something by showing a lot of examples of it being true? No, not unless we have infinitely many examples. Then we're good, right? No, doesn't matter how many examples you have. Example, all primes are odd. 3, 5, 7, 11, I could go on forever showing you that every prime is odd. What did I forget? 2 is a prime. So you never know when you're trying to prove stuff, even if you try a lot of cases and you want to say, obviously it's true, look at all these cases. What if you're just not clever enough to think of the 2 case? There might be one stupid little case that happens to disprove your whole theorem that you just happen to not think about. In this case, 2. So, you remember what a conjecture is? A conjecture is a statement that mathematicians think is true because it keeps looking that way, but we haven't found a way to prove it yet. Just like mathematicians might have thought all numbers were prime because we happen to not think of 2 yet. So, the Goldbach conjecture, this is still a conjecture, still unproven. If one of you comes up with a way to prove it, you'll be famous. So, you have homework tonight. Anyways, the Goldbach conjecture, what does it say? It says every even integer greater than 2 is the sum of 2 primes, or can be expressed as the sum of 2 primes. What do we mean? Let's look at the first even integer greater than 2, namely 4. 4 I can write as 2 plus 2, both primes. Good. 6 is 3 plus 3, both primes. Good. 8 is 5 plus 3, both primes. Good. 10 is 7 plus 3, both primes. Good. 12 is 7 plus 5, both primes. Good. 14 is 11 plus 3, both primes. Good. 16 is 13 plus 3, 18 is 13 plus 5, 20 is 13 plus 7, etc., etc. We have computers cranking away at this. They've gone billions and billions of numbers down there, and they still haven't found a case where it doesn't work. So it seems like it works. We're very confident that this is true, yet we haven't been able to prove it's true yet. So, just a quick proof, and you'll be a big shot. Okay, so a lot of this chapter we're going to be focusing on proofs, and the hard facts, the reality of working with proofs is there is no surefire way to prove something. Now, I'm going to go through some proofs with you to try and give you a high-level way of approaching. We're going to start out with direct proofs, for those of you who know, like, proof by contradiction. We're going to start with direct proofs, and I'm going to give you some basic strategies that you can utilize to help you understand how to prove, and then I'm going to show you where, no matter how many strategies I give you, there comes a point where your brain just has to figure it out. So we'll do a really simple proof to show this in action. So let's say that we're trying to prove that the sum of 2 even integers is even. Okay? Any statement you're trying to prove, any theorem you're trying to prove, is somehow an implication. You remember what I mean by an implication? It's an if-then statement. Whatever your statement is, figure out how it's an if-then statement, figure out what the antecedent is and what the conclusion is, and write it as an if-then statement. That's step number 1 to help you prove. So the sum of 2 even integers is even. What is it saying? It's saying if a and b are even integers, then a plus b is even. Okay? So that's going to be one of the things on your homework. We're going to give you just a ton of statements, and you're going to rewrite them in if-then form to make sure you know how to do this. Any questions on the first part, or on how this is the same thing as this? All right. So once we have it written in an if-then form, our first line in our proof is going to be to assume the antecedent is true, and the last line is going to be therefore our conclusion is true. So we have if a and b are even integers as our antecedent. So the first line is let a and b be even integers. Our conclusion is then a plus b is even. Therefore, our last line of our proof is therefore a plus b is even. Step 2. That's basically half the proof, right? Easy peasy. All right, next step. the next step we call unraveling definitions. So plug in all the things you know based off the definitions you're given. So I know that A and B are even integers. What does it mean for A and B to be even integers? They're divisible by 2. So since A and B are even, then 2 divides A and 2 divides B. But wait, there's more. We know what it means for 2 to divide A and 2 to divide B. What does that mean? Well, since 2 divides A and 2 divides B, then there must exist some integers, call them x and y, such that A is equal to 2x and B is equal to 2y. Right? Okay, we used all our definitions. Now we're stuck at line 3. Well, shoot. But we can still go to the bottom and plug our definitions going up. So let's do that. We said, therefore, A plus B is even. What does it mean for A plus B to be even?
It's divisible by 2.
Yeah, so then we know we've got to prove this line if we're ever going to prove this line. Right?
Yeah.
So we've got to prove then 2 divides A plus B somehow. What does it mean for 2 to divide A plus B? Well, it means that there exists some integer c such that A plus B equals 2 times c. Right? So if I can rewrite A plus B as 2 times something, I know I'm done. So I've got 6, and I've got 3, 4 and 5 are the bridge between. 4 and 5 is where you, on your own little lonesome, have to come up with a way to connect these two things. Now you'll notice line 6 is talking about A plus B, and in line 3 we have an A and we have a B. What's the natural thing to do? Add the A and the B together and see what comes out. I mean, ultimately that's what you're trying to do, show A plus B is even. So line 4, let's look at what A plus B is. Then A plus B is, 2x plus 2y. Oh, that's 2 times something. Call that something C, and then you have this. And we're done. Any questions? You just need to stare at it for a sec? You're taking way more than a sec. You're taking like 20 of them. We good? Ready to move on? Any questions? All right. Next. So let's do one having you guys do it all. All right. So let A, B, and C be integers. Then if A divides B and B divides C, then A divides C. Right? In other words, we're showing that if A divides B and B divides C, then A divides C. That's what we're trying to prove. So what am I going to write here for my if-then statement? How many H's?
Let A, B, C.
If A, B, C are integers.
In the integers set.
If A, B, oops. If A, B, and C are integers, you okay with that? Are integers? I spell R weird. And I spell integers even weirder. Zzz. If A, B, and C are integers, or are in the set of all integers,
And A divides B and B divides C.
and A divides B, and you guys like and, B divides C,
Then A
Then
divides
A
C.
divides C.
then A divides C. Good enough. An if-then statement. Right? So now what's the first line of my proof?
Let
A, B, C
be
be
integers.
integers.
Let A, B, C be integers such that A divides B and B divides C. Right? Okay. Should we go down to our bottom line, or should we just keep working with it and see if we can figure it out?
We can keep working with it.
Do we have definitions?
I don't know. Do we have a definition for that?
Okay.
Yeah.
Yes.
We sure do. All right, Rhoda. What's our definition? What does A divides B give us?
I mean,
Tell me this next line to write.
Oh, wait. That means there exists an integer.
So then there exists x and y. There's going to be two of them. We can do one at a time. Then there exists an integer
That
such that
x times a equals b.
a times x is equal to b. Perfect. That's exactly right. And we can do the same thing for this one, right?
Yeah.
Yeah.
So then there exists, now I'm just going to do it all in one go, now that you're comfortable with it. So then there exists integers, call them x and y in z, such that I'm going to write the b's equal to, you okay if I write it this way? B is equal to a times x, and c is equal to b times y.
Yeah.
Anything weird there? Okay. Well, that gives us that. Now what?
Well, what do we have to get to? What we have to get to is
Well, we can go plug that in. Therefore, what are we trying to get to? A divides C.
a divides c
How do we know when we've got A divides C?
is when we've got an
It's when we find some integer, we'll call it Z, such that
C.
A times Z is equal to C. Or C is equal to A times Z. It's probably a better way to say it. Right? So we just gotta find that darn old Z.
You can multiply, so in the equation b equals ax, multiply each side by y. And then you'll have b times y, which is c, equals a times.
You got the right idea, but you're overthinking it. So over here I've got C equals something. Up here I've got C equals something. So then
Why don't you just put in
C
ax
equals
for b.
B times Y. We can put in AX for B
Yes.
is equal to A times X times Y. Right?
Now we have a times something, which is
C is equal to B times Y.
Yeah.
And B is equal to A times X.
Oh, okay.
So C is equal to B times Y is equal to B times Y.
Okay.
Mm-hmm.
Right?
Yeah.
For let Z equal X times Y. And we're done.
Wait, how did you get z equals x times y?
I'm just going to call X times Y Z. I'm just relabeling
What
it.
if that doesn't work?
I can always call a number anything I want. Huh, Ann?
Oh, I got you. Y is equal to n.
Why'd you call me Robert?
Okay, I got it. I got it.
Everyone see the connections?
Yeah.
Anything weird? Anywhere where it feels like we cheated?
Wait, you left out the a. The a? I'm confused.
C is equal to A times XY. We called XY Z, so C is equal to AZ.
Yeah.
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 Easy. We good?
I
Yep.
think so.
You think so? That sounds pretty confident. That sounds like I incontrovertibly showed it was true to you.
I think so.
Because, yeah, I think I proved it. Doesn't sound very incontrovertible. Is there anything weird that you want to discuss better? Or you just want to see more proofs?
See more proofs.
All right, we'll just continue with proofs. Okay, let's do another one. Since you guys take so long to do them, I filled in all the rest myself.
Well,
Oh, shoot.
All right. No, mostly I just want to say it. Okay, so next one we're going to do. We're going to prove that if x is an integer such that x is greater than 1, then x cubed plus 1 is composite. Kind of weird, right?
Mhm.
How come I can't ever get a prime that looks like that? We'll prove why. All right, so we have our if, antecedent, then conclusion. Start out with our if. let x be an integer such that x is greater than 1. Therefore, x cubed plus 1 is composite. Okay? Now, this one we're kind of stuck because we don't really have a definition to plug in here. We do have a definition to plug in here, but it doesn't really help us. So even though we have these great strategies for plugging in up and down, sometimes they don't get you far, and you just have to figure out how to do it. And here's an example. All right, so we're trying to show that x cubed plus 1 is composite. What does it mean to show it's composite? We need to find an integer between x cubed plus 1 and 1 that divides x cubed plus 1. Right?
Yeah.
Okay. So, first off, here's the first major trick to the problem. Notice that x cubed plus 1 can be rewritten as x plus 1, x squared minus x plus 1. Now you might think, why on earth did I think to factor this thing? The reason I thought to factor this thing is I need to find two integers such that when I multiply them together, I get this. That's how you show something is composite. If I say, prove to me that 32 is composite, what do you start doing in your head? You start thinking, oh, what two integers can I multiply together to get that? And you might think something like 8 and 4.
Yeah.
So I want to express this as a product of factors to help me show that it's composite. The exact same thinking here. I want to show that this thing's composite, so I want to factor it. I want to split it into two things.
Why is it minus?
Just multiply it out. X multiplied through gives me x cubed minus x squared plus x. 1 multiplied through gives me positive x squared negative x plus 1. Did you see that in your head, or should we write it? Multiplying the x through first gives me x cubed minus x squared plus x. Then putting the 1 through gives me x squared minus x plus 1. Add them, x squareds go out, x's go out, you have x cubed plus 1. Good?
Yeah.
Okay. So, notice that since this integer is equal to this integer times this integer, then x plus 1 divides that thing.
Yes.
So I found some number, just like we were looking at 32. I can split 32 into 8 times 4, right? So I found one of these. So one of these numbers, whichever one I want, this one's obviously simpler to work with, divides 32. So I'm saying 4 divides 32 or something to that fact, right? Okay. So I showed that x plus 1 divides that thing. It remains to show that x plus 1 is between 1 and x cubed plus 1. And once I show that, I'm done. Right?
With the proof?
Yeah. I'm trying to show that this number is composite. How do I show it's composite? I need to show that there's an integer, namely x plus 1, that divides it, and that's between 1 and the number itself.
Yeah.
Okay. Yeah.
Does that make sense?
Yeah. Yeah.
So you understand that if I can show
Oh.
that this inequality is true, are you guys okay with this string of inequalities? 1 less than x plus 1 less than x cubed plus 1?
Yeah.
That's okay? Okay, so if I can just show that this string of inequalities is true, then I'm done, right?
Yeah.
Is there any, is that weird?
No, it makes sense.
There's two parts to showing C's composite. I need to show A divides C, and I need to show 1 is less than A is less than C.
Yeah, it makes sense.
In this case, I'm showing x plus 1 divides C, x cubed plus 1. That's the first part, we've already got that. Next I need to show 1 is less than x plus 1 is less than x cubed plus 1. So I've already shown this, now I just need to show this, and it's composite. And we're done. Good? Am I blocking your view?
No.
Okay. So, we need to show this. And we can show this in two steps. First I can show that x plus 1 is greater than 1. And then I can show that x cubed plus 1 is greater than x plus 1. And then I've shown the whole thing. Right?
How do you do that?
It's a secret. I'll never show you. Ready? since x is greater than 1, how do I know x is greater than 1?
Because it's in the statement.
It's what we assumed right at the beginning. Let x be an integer such that x is greater than 1. Sine x is greater than, oh, we're right here. We're on since, not sine. Since x is greater than 1, then adding 1 to both sides, the inequality is still true, right?
Yeah.
X is greater than 1 means x plus 1 is greater than 1 plus 1. Therefore, x plus 1 is greater than 1. You good with that logic there? Nothing weird?
Why did you do that 1 plus 1 then?
I was just showing you, I'm taking this and adding 1 to both sides. So x plus 1 is greater than 2, which is obviously,
Which means
if it's greater than 2, it's greater than 1.
Oh.
Okay, click.
Yeah.
Awesome. Alright, so we're good with this line that x plus 1 is greater than 1.
Wait, did we ever define greater and less than symbols?
Nope, we said that that's one of the things we're going to assume we already know. Basically, everything in the field axioms and the positivity axioms, we're assuming we already have that.
Okay.
Okay. So x plus 1 is greater than 1. Alright, next. Sine x1, greater than 1 I mean, and that's supposed to be since. Since x is greater than 1, then multiplying both sides by x is still true, right?
Yeah. Yes.
And multiply both sides by x again, and it's still true, right? So I have x cubed is greater than x squared is greater than x, and x is greater than 1. Oh, I didn't need to go that far. I have x cubed is greater than x squared, and x squared is greater than x, or in other words, x cubed is greater than x. You good with going from these two statements to this one statement?
Yeah.
And then add 1 to both sides. And it's still true. And we're done. I showed that x plus 1 satisfies this inequality. Any questions on that proof? This one's for sure going to be on the test maybe. So make sure you know it. For sure maybe. Okay. Alright. What's next? Oh, and if and only if. Have we talked about the double F? If and only if. So it's a shorthand that we use all the time in math. If I say if x, if y, that's shorthand for x, if y, and x only. Only. If y. X if and only if y. Another way to think about it is they're logically equivalent, but we're going to show that let's rewrite it like this real quick. X if y is the same thing as, which way does the implication go?
X implies
Y implies x. And then x only if y is x implies y. So let's make sure that these both make sense in our head before we continue. Let's see what this says. I'm going to put on my shoes if I'm wearing socks. Means if I'm wearing socks, then I'm going to put on my shoes. Okay? The only if one, what's the example I like to use for that? There's a good one out there. Oh, it's if, I'll just say it. X is there's smoke only if there's fire means if there's smoke, then there's fire. Right? So you see how x only if y is x implies y, whereas x if y is y implies x. Are we good with that? Am I just wasting my breath here?
Makes sense.
So when I say x if y, that means x if y and x only if y. That's short for x if and only if. y. That's how we mean it. So we've got this statement here that says, let x be an integer, then x is even if and only if x plus 1 is odd. What do we mean? We mean if x is even, then x plus 1 is odd, and if x plus 1 is odd, then x is even. So these if and only if proofs is kind of like you have to do two proofs in one. Okay? So let's set it up and I'll show you what I mean. So let x be an integer, and then you're going to notice that we do an arrow like this and then an arrow like this. So when I put an arrow pointing this way in my proof, what I'm saying is I'm going to show that this side implies this side, and then when I put an arrow pointing this way in my proof, I'm going to show that this side implies this side. So let x be an integer. Next I'm going to assume x is even. I'm going to assume x is even and show that implies x plus 1 is odd. And then when I get down to this arrow, I'm going to assume x plus 1 is odd and show that implies x is even. And then we'll be done. You understand big picture how this is all going to come together?
Yeah.
Awesome. So assume x is even. What does it mean for x to be even?
It's divisible by 2.
It's divisible by 2. What does that mean?
There exists an integer.
There exists some integer y such that x is equal to 2y. Perfect. If x is equal to 2y, what is x plus 1?
2y plus 1.
Which is?
Odd.
Perfect. So if x is even, x plus 1 is odd. Now let's do it the other way. Assume x plus 1 is odd. What does it mean for x plus 1 to be odd? It means that there is some integer y such that x plus 1 is equal to 2y plus 1. Right? Then, what does x equal?
2y.
How'd you do that?
Because you subtract 1 on both sides.
Genius. So just subtract 1 from both sides. X equals 2y, which means 2 divides x, which means x is even.
You know, in my head, I was just like, you can't subtract both sides by 1 because I'm so used to our logic course. You can't just subtract 1 from both sides.
You can plus negative 1 to both sides.
Yeah.
And there you go.
Yeah.
Okay, so therefore x is even if and only if x plus 1 is odd. Good? Easy peasy. On to the next one.
Yeah.
Okay, now we're going to teach you how to utilize your past proofs. You don't need to reinvent the wheel every time you do a proof. Let's see an example that seems like it might be hairy, but turns out it's real easy. If A, B, C, and D are integers such that A divides B, and B divides C, and C divides D, then A divides D. That sounds like a nightmare. Let's prove it. Let A, B, and C be integers. I missed my D. We need an A, a B, a C, and a D. Be integers such that A divides B, B divides C, and C divides D. Assume our antecedent. We're going to show that applies our conclusion. Since A divides B and B divides C, then A divides C. How the heck do I know that?
Because you just proved it.
Ah, because of this proof right here. This proof says if A divides B and B divides C, then A divides C. And now we're going to use that proof again. Since A divides C and C divides D, then A divides D.
Right.
And we're done. Now, you could have gone and proved that like this. You could have plugged in the definition for all those things and solved it like that and had a nice, I don't know, 10-line proof. Or you could just use what you've already done and save yourself a headache. Good?
Yeah.
Any questions on this proof? Any question how we were using this proof to do it? You cold? You can turn off the AC if you want. Next proof. So the point in this proof is to show you how we sometimes handle strings of equations and inequalities in a proof. So we're going to prove that if x is greater than 2, then x squared is greater than x plus 1. Understand what we're trying to prove?
Yep.
All right. assume the antecedent, let x be an integer such that x is greater than 2. I forgot to say integers up there, but they're integers. Then, take this inequality, multiply both sides by 2, and you get x squared is greater than 2.
Yeah.
You okay with going from this to this? X times x is greater than 2x, and 2x is greater than 2, so x times x is greater than 2.
Okay.
Okay, now here's the real point of why we're doing this. Because ultimately I'm trying to show x squared is greater than x plus 1. Why did I do is greater than 2 there? Ignore this part.
You want to just leave that as 2x?
Yeah, I don't know why I did that. Weird. Okay. So then, x squared is greater than 2x, right?
Yeah.
2x is equal to x plus x. X plus x is greater than x plus 1. Which is, why did I do x plus 1 again? I have no clue why I keep putting random lines in here.
You did it twice. Wait. You don't know that x plus x is greater than x plus 1?
Yeah, how do I know that x plus x is greater than x plus 1?
Because x plus.
Because x is greater than 2.
Because x is greater than 2. That thing's a lot bigger than that thing, and that thing's the same size as that thing. Right? Therefore, x squared is greater than x plus 1. But the point I was trying to make with this proof isn't so much the result as it is when you have strings like this where you want to keep going is equal to, is greater than, or equal to, all in one string, that's okay to do in your proofs. And it's very common to do that.
What happens if you get confused of if you ever think that it's confusing what you do, then should you just not do it? Because you could get confused on thinking that that's all referring to the top line instead of going in a
100%, you should not try doing a shortcut that confuses you. Shortcuts are to save you from doing something tedious. If it's still an exercise for you to write it out the long way, do that. It's only once it becomes tedious that this is fine. Right? Write for you, write for your classmates, don't write for me. That's a common piece of advice that, oh shoot, I need to move my camera. Missed the end of the proof. Hold on there. How did I have it last time? I have it like that? Oh, I tipped it the wrong way. That messed with my brain for a second. Okay, we'll try and get just that little bit. Oh well, we've seen that. Okay, anyways. So, doing this is perfectly fine in your proofs if it gets to the point where you feel like dragging it out line after line is becoming tedious. Oh, I was saying write for your peers. Write for the people to your left and your right. That's good common advice for people first writing proofs is think about, could Rhoda understand what you were writing? If Rhoda could understand what you were writing, you're good. If you're making some leap that Rhoda couldn't follow, chances are, no, you're making a bad leap. Go back and explain it better. So don't write for me, write for these guys. And then I'll be fine. Maybe. Rhoda's pretty quick, so I'll have to try and keep up.
Yeah.
All right. So that's the end of section 5. Section 6. Section 6 is all about counterexample. The point in section 6 is sometimes it's a lot easier to disprove a statement, prove a statement's false, than to prove it's true.
Right.
Because all you have to do is find one example where it doesn't hold, and then you've proven it. So if I make the statement that every prime is odd, is that statement true?
No.
No. If you can find one example of a prime that's not odd, namely 2, then you're done. You've disproved the statement. So I want you to do that now. Here's a statement I want you to disprove. Prove that if A divides B and B divides A, And then A equals B.
A divided by B and B divided by A equals B.
Yeah, start working on that, see if you can figure it out. How many of you think you've got it?
I'm confused. Are you saying find an example where it doesn't work?
Are you trying to prove that does work? I'll give you a hint. It's not true. So yeah. You just need to find one example where it doesn't work. If you can find one example where it doesn't work, then you're done. That's how you prove it's false. So you're doing proof by counterexample. You're proving that this is false. This is not a good theorem. If you were a professional mathematician and someone came to you with this theorem and they says, look, I proved this, you don't even need to look at your work. You can look at this and say, actually, it's not true. See? So I don't know what you proved, but you cheated. Right? So I might give you something like that on your test, say, prove this, and then if I see some big proof instead of some small counterexample, then I say, no, sorry. Thanks for trying, but it doesn't work. It's something I did on one of my tests once. Spent forever trying to prove something, and I was just supposed to come up with a quick counterexample. they're just integers.
Then does it work if it's -1 and 1?
Yep, and that works. That's what you did? Good. Yeah. Just pick A and B to be negatives of each other. Negative 10 divides 10. 10 divides negative 10. Is 10 equal to negative 10?
No.
No. So how do you disprove it? Observe 10 divides negative 10 and negative 10 divides 10, but 10 is not equal to negative 10. Disprove it. All right, so moving on now to Boolean Algebra. That was all section 6. Section 7, Boolean Algebra. Boolean Algebra, I kind of force you to go through when we go through logic, just because I'm not going
All
to...
of section 6.
Yep,
Hard to see that.
don't worry, there's way more homework than there is material. So, you'll get your fill. Okay, so Boolean Algebra. First off, what is a Boolean? Anyone know?
A value that's true or false?
It's a value that's true or false. That's what a Boolean is. It's a true, it's something that you can evaluate to true or false. When we're talking about logic or when we're talking about statements in logic, we're talking about Booleans, things that can be evaluated to be either true or false. And so when you were doing logic and you were thinking about X and Y as representing statements, and now when we think about them in Boolean algebra, we're going to think about them as representing Booleans. It's all the same. Everything you do in logic and everything you do in Boolean algebra, it's a one-to-one relationship. They're identical. They're the exact same thing. Okay? Once you realize that, everything we did in logic is the exact same thing we're going to do here in Boolean algebra. No difference. So let's crank through it. So a Boolean is a value that's either true or false. And we have operators we can apply on Booleans, just like we have operators that we can apply to numbers. If I have a number 10, and I apply a negative to it, what does it give me? Negative 10, right? Similarly, if I have a Boolean true, and I apply the not to it, what does it give me?
False.
False. If I have a number 10, and I add 1 to it, what does it give me? 11. Similarly, if I have a true, and I or a true with it, what does it give me?
True.
It gives me a true. It's an operator. It takes two Booleans and it spits out a Boolean. Just like plus takes two numbers and it spits out a number. It's an operator. That's what operators do. They take two things out of your domain, whatever you're talking about, and spit one out. That's what binary operators do. Unary operators take one and spit out one. So another unary operator that you're used to is like 10 squared. Squared would be a unary operator. What does it give me? 100. Takes in one number, spits out another number. Negative was another unary number. It takes 10 and it spits out negative 10. I don't know how to write that without just doing negative again. But, so you're used to these kinds of operations, you're used to these kinds of things. You just need to know how to evaluate them now. You need to know how to plus in order to do arithmetic. You need to know how to and, or, implies, etc. to do Boolean algebra. So let's go through it. And make sure you remember everything. So if I have two Booleans, x and y, if they're both true, then x and y is true. If they're both true, then x or y is
True.
If they're both true, then x implies y is.
True.
If they're both true, then x is logically equivalent to y is.
True.
And if they're both true, then not x is false. This one has nothing to do with y, right? All right, next. True and false is?
False.
True or false is?
True.
True implies false is?
False.
True is the same as false is?
False.
And not true is? Good? All right, continuing. What's this? What's this?
True.
What's this?
True.
What's this?
False.
What's this?
True.
Good? And the last row.
False. False.
True.
True. False implies anything is?
True.
True.
False.
True, they're the same. Is false the same as false?
Yeah.
Yes. That's what the double arrow means. They have the same value. And then finally, not false is?
True.
Whoa, we messed up somewhere. Oh, no, man. That was weird. Okay, so that goes over all the basic logic operators, and or implies, logically equivalent, not. Now, let's just do it again for the fun of it. Just kidding. We're going to do some of it the same. So let's really quick fill these out. This column I'm going to put not x, which is then going to be true, true, false, false. This column I'm going to put not y, which is false, true, true. Maybe before we go crazy with this, well, we can do the and real quick and then I'll explain what we're doing. Do the and real quick, we get false, false, true, false. Right? I changed the order to make sure that you're actually thinking about it instead of memorizing stuff. Okay, so now the next one, what we're showing in this truth table, we're actually doing a proof. The proof that we're doing right here, and this is a proof with a, what do we call these?
Truth table?
Truth table, thank you. We're doing a proof with a truth table, and we're proving that not x and y is equal to not x or not y. That's what we're proving. When you're told to do proofs like this, you use a truth table. How do you show that they're equal? You show that they always give you the same value no matter what combination. Right, so let's do just a really quick proof right out the door. Say I'm supposed to prove that not x is equal to x. How do I do that? I set up a truth table. Here's x, here's not x, here's not x. X can be true or false. If x is true, not x is false. If x is false, not x is true. And then this just nots this. So that's true, false. These two columns have identical things no matter what the input was. Therefore, they're the same. See, we have a cool way of making sure Boolean expressions are always the same because it's real easy to plug in all the values. They can only be these. We can't do the same thing if we wanted to show that 2x is equal to x plus x. We couldn't just go through and plug in every possible number and check every case because there's infinite numbers. But since there's only two Booleans, then we can plug in all the cases and make sure no matter what we plug in, it's always the same. If there were only two numbers, then we could check this that way, but there's more than two numbers, so we have to have different ways for proving expressions like this. But proving Boolean expressions are equal is the most straightforward way to do it. Plug in all the combinations, make sure it always spits out the same thing, and you're good. Make sense?
Yeah.
So let's go to this one. Now this one is, we're proving how to distribute a not over an and. If you have not x and y, that means you have not x or not y. Let's come up with an example. If I tell you that it is not the case that I am holding a green and pink marker, what does that mean? If it's not the case I'm holding a green and pink marker, it means either I'm not holding a pink or I'm not holding a green. Right? If I'm not holding both, then I'm not holding one or I'm not holding the other. Make sense? That's what this is saying. If not x and y, that means not x or not y. And we're going to prove that. Just trying to give you some intuition first. So let's actually prove it. So not x and y is just the negation of and, right? So that's just going to be, what is it? True. True. False. False. True. All right. So now let's look at this one. This one is ORing the negations right here. So we're ORing these two columns together. Make sense?
Yeah.
So true or false is?
True.
Where are we? True or true is? False or false is?
False.
False or true is?
True.
And notice, this column and this column have identical values. Therefore, they're logically equivalent. This and this are the same. Okay? So now let's do it the other way. So when you distribute not over and, it's not or not. Similarly, when you distribute not over or, it's not and not. So let's try and make sense of this. If I say that I am not holding the green or pink marker, then that means I'm not holding either of them. I'm not holding both. Right? If I'm not holding the green or pink marker, I'm not holding either of them. If I'm not holding X or Y, I'm not holding X and I'm not holding Y.
Yeah.
Make sense? So, let's fill that real quick. Just spit it to me.
False, 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 true, 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 false, true, true, false. False,
Now?
true,
Yep.
true, false, false, true, true. Oh, I was looking at the wrong ones again. False,
False, false,
true, false,
Alright, now we're anding these two together. False and false is?
false,
true. No, false.
False and true is?
false,
False.
True and true is?
true,
False and true is?
false.
And there we have it. They're the same. Ta-da. Okay. So let's list out a bunch of expected properties. And all of these things can be proved with truth tables, but we're not going to prove them all. So all the properties that they have, x and y is equal to y and x or y is equal to y or x. What does that mean?
It's commutative.
Commutative, yes. And is commutative. It doesn't matter what order you do it in. How would you prove this? Make a truth table. Show that those two are the same. Or is commutative. How would you prove this? Make a truth table. Show that they're the same. Next, we want x and y and z is equal to x and y and z, and x or y or z is equal to x or y or z. What does that mean?
Associative.
It's associative. And and or are associative. Do you understand the difference between what this and this is saying?
Yeah,
Yeah.
it's saying first do this, then this.
Yeah, this is saying and these together, and then and this. Where this one's saying and these together, and then and this. Similarly with the or. So let's plug in an example with actual values to see it in action. In other words, I'm saying true and false and true is the same thing as true and false and true. What's true and false?
False.
False and true, and that is false. Same thing over here, false and true is false.
And true.
True and that still gives me false. Same thing.
Okay.
The same way that we look at addition as being associative, 10 plus 5 plus 2 is the same thing as 10 plus 5 plus 2. 15 plus 2 is equal to 10 plus 7. 17 equals 17.
Yeah.
Same thing. Alright, so and or are commutative, and or are associative. Let's continue on writing. That marker seems like it's giving out a little bit. Next, we have x and true is equal to what? Whatever x is. If x is true, this is true. If x is false, this is false. Make sense?
Yes.
And x or false is equal to
X.
x. If x is true, this is true. If x is false, this is false. So what is true?
What?
What is true? The same way you said up here, this was commutative property. This was, they had the associative property. What do we call true? If ending with true doesn't change it, it's the
Identity.
additive identity. If we want to make up a word, it's the identity for the AND operation. The same way that 0 is the identity for the plus operation. X plus 0 equals X is the exact same thing as X and true equals X is the same thing as X or false equals X is the same thing as X times 1 equals X. Those are probably the identities you're most familiar with. We'll play with some other fields in this class so you can get used to other identities. Alright, one more properties. We already proved this one, but we'll throw it up here. Not X is equal to X. The double negation gives you back where you started. And then how to distribute. Maybe we'll prove this one. In a truth table, but first we'll just list out all the properties and then we'll come back and do this one. So, X and Y or Z is the same thing as X and Y or X and Z. Similarly, and X or Y and Z is equal to X or Y and X or Z. So that's how you distribute and over or. It's somewhat similar to if I have X times Y plus Z, that's equal to X times Y plus X times Z. We're doing a similar thing here. X and Y or Z is X and Y or X and Z. You see how it's doing the same thing? Distributive property. So that's how we can distribute ands over ors and how we can distribute ors over ands. And we'll create a truth table for this one to show that one because that one's not as intuitive. This one, X and not X, what does that equal?
False.
False. The sky's blue and the sky's not blue is always false. A statement and its contradiction can't be true. Similarly, X or not X is true. The sky's blue or the sky's not blue. Right? You're doing your test. Your teacher says, what's the answer? You say the answer's 6 or the answer's not 6. It's right every time.
Right answer.
Oh, thank you.
Doesn't even matter if you're doing a history test. Who was the first president of the United States? 6 or not 6?
That is so true.
All right. And then the last one, we already proved this one, De Morgan's. It's just how to distribute a not. Not X and Y is equal to not X or not Y. And not X or Y is equal to not X and not Y. Any questions on any of those properties? It's just all obvious. Okay, then we'll just do the proof of one of these. I don't care which one, just to see it, and then we'll call it good.
Do the one that you were saying to
Distributive property.
Yeah, I'm just saying there's two. You want me to distribute and over or do you want me to distribute or over and?
Or over and.
Or over and. That's probably the less intuitive of the two. If you want to think about or as addition and as multiplication. Because you can't distribute addition over multiplication, you can only go the other way. in algebra, on real numbers. Okay, anyways. So notice that what we're proving has, well, let's just write it and then I'll tell you. I was distributing or. You know what, we'll just do them both.
Don't you have to have more rows for this one?
Because you have 3 variables.
Exactly. That's why I said that I was going to bring up after I finish writing. All right, let's make the biggest truth table of our lives. Now, first off, notice with x, y, and z, how many possible combinations of true and false can I get?
Like 8.
8, right? I could have all true, the first true, this false, etc., etc. So let's just list out the combinations, and I'll just use the common trick, so I don't have to think about what they all are. Okay, here's all the possible combinations of true and false that we can have. Now notice, every time we add another variable to our expression that we're evaluating, we have to double how many rows we have. Which means there comes a point where this becomes impractical, and you can't prove everything this way. It blows up exponentially, which means even once it gets sufficiently big, computers can't even keep up. Exponential growth is a terrible, terrible thing. You can't keep up with it. So this is 2 to the x, where x is the number of variables. So it blows up, which is why we have other methods of proving, plus we can. That's a logic discussion. Never mind. Doesn't matter. All you need to know is every time we add a variable here, then you need to double how many rows you have. So for one variable, you have 2. 2 variables, you have 4. 3 variables, 8. 4 variables,
16.
5 variables,
32.
6 variables,
64,
7,
128,
Keep going.
8,
256,
9,
512,
10.
1004.
So with just 10 variables, you already have to have over 1,000 lines. 20 variables, you have to have over 1 billion. 30 variables, you have to have over 1 billion. Yeah, blows up. Yeah, bro. Just 30 variables, and I have to have 1 billion lines to do it? Crazy. Exponential growth. Very fast. Okay, so let's just grab the bull by the horns and do it. So the first one.
What is
True and true is,
true?
True.
or true is,
True.
true. True or true and true or true is.
True.
Alright, so it worked in the first case. Phew. Next, let's see. True and false is.
False.
True or false is.
True. True.
We have
True and true.
true or true and true or false.
True. True.
Should we try motivating this in our mind first? Let's make intuitive sense of these statements, then we'll continue. Sorry, I should have done that first. So let's say, I need it in the inclusive or. So let's say a university says that you either have to take calculus to get into their school, or you have to take physics and chemistry. So you have to take calculus or physics and chemistry. That means you have to take calculus or physics and calculus or chemistry. That one doesn't sound that intuitive, does it?
No.
No. What's another way to make it more intuitive? If anyone can think of some statements, let me know. I don't know. It still makes sense to me. Take calculus or take physics and chemistry means you have to take calculus or physics and calculus or chemistry. You can do calculus and chemistry in both these, or just do that.
Okay.
Is that making more sense? Let's just do the truth table then.
Yeah.
And maybe some intuition will come along the way as we do it. Okay. So, let's see. You take calculus, but you don't take, well, we won't even say that. That will be too wordy. Okay, so over here, is it true or false?
True.
True. How do we know this is true? Just look at x. If x is true, we don't care about that. You took calculus, you're in.
Oh, okay.
Over here, true or false? True. You took calculus, so you have a true in both these. True or anything is true. True or anything is true. True and true is
True.
true. All right, let's look at this one. True or false?
True.
Let's move that true. It's true. How do you know?
Because we took X's.
You took calculus. What about over here?
True.
Same thing. You took calculus.
Okay.
All right.
Nice.
Next one. You don't take calculus, but you take both physics and chemistry.
That's true.
Are you in?
Yeah.
Yeah. What about over here?
Yeah. Yeah.
Yeah. Okay. You only take physics.
Nope. That's false.
No, this is false. False or false is false. Same thing over here.
Took one, but you didn't take the other, which makes them false.
Yeah, which one was false?
Why?
Or Z? Y is the only true one. So this is true, but you had to have this true and this true. So that's false. Doesn't work. And then if you only took chemistry, false, false. And then if you didn't take any class, then you're definitely in.
Did you get a pick up? You did that, Rhoda. I'm in discrete.
Okay, now let's look at this one. This one is, they're saying you have to take calculus and physics or chemistry. So they want you to take calculus and a physical science. So you have to take calculus and physics or chemistry to get in. Alright, if you take all three, are you in?
Yes.
Yeah.
Alright, let's look at here. You have to take calculus and chemistry, or you have to take calculus and physics.
Oh, yeah.
Or other way, calculus and physics, or calculus and chemistry.
True. True.
See, that one makes more sense, right?
Yes.
Distributing and over or makes more sense than distributing or over and. It's hard for us to think of. Okay, once again, that's true. Okay, next one.
True.
You sure?
Yes.
Okay.
True.
True. True.
False.
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 False. Why?
Because they didn't take cat.
Because they didn't take either of those.
Yeah, they didn't take either of the sciences, or in other words, this whole thing's false, so this one's always false. And then over here, that's false because that's false, that's false because that's false. So, false, false. Next.
The rest are false because they didn't take any chemistry.
And the next ones are all false because they didn't take a math. So this side's always false, and then the left-hand side of both these is always false, so the whole thing's always false. It's all false from there on out. You got it. So that's how you do proofs using truth tables. We just prove that this is the same as this, oops, this is the same as this, and this is the same as this. Boolean algebra. Good? So that should be that. Now all that's left is, did you have questions on your homework from last week?
I did on the.
Oh, I had a question or two.
Oh, mine's on the extra credit.
Me too.
So I didn't know how to do that.
The extra credit?
Yeah.
I'm gonna have to see someone's homework and see.
Okay.
That's fine. You don't have to do the
I
extra
need-
credit. Does someone have a solutions manual? Something that I can look at that's my own beautiful work?
You didn't do all the
You want me
solutions
to
for that one.
homework that?
I what?
You didn't do all the solutions for that one.
To what one?
Do the extra credit question.
Oh dang, don't
Yeah,
give
it
up
is.
clock.
You just did A and B.
Oh.
I could do C.
Oops.
I tried to do the other ones though.
I don't get C.
I couldn't figure some of them out. Oh, I need pulled up.
Well, not worried about the extra credit. Did anyone have questions that weren't extra credit problems?
I did. 4.2e.
4.2 E. If
Oh,
E then
I
A.
had the same question.
It's very possible I made a mistake on this, so.
That's why I was confused.
Mm.
4.2 E. This year is divisible by 4. This year is a leap year. If this year is divisible by 4, this year is a leap year. Or
That, and you said B implies A. But it could be both.
below, you will find pairs of statements A and B. For each pair, please indicate which of the following 3 sentences are true and which is false. If A, then B. If B, then A. A, if and only if B. Oh, so do they imply each other? If this year's a leap year, then it's divisible by 4. If this year is divisible by 4, is it a leap year? No. You skip a leap year every century, I think, or every 2 centuries. So, my answer's right.
So,
Okay, wait.
what about false?
If it's a leap year, then it's divisible by 4. That's true. If it's divisible by 4, that doesn't mean it's a leap year.
So it's B implies A.
Because you skip a leap year every, I don't remember how often, but for example, in the year 2000, it wasn't a leap year. That's one of the years that we skipped.
Okay.
So it's B implies A, not A implies B.
So it's B implies A. If B, then A.
I still don't get that. B implies A for that statement.
If it's a leap year, then it's divisible by 4. Every leap year is a multiple of 4.
You just said we skipped one though. Oh, you mean like, okay, for some reason.
So the
like,
year-
first 5 digits would be-
2004, 2000, 1996. These are all divisible by 4. This was a leap year, this was a leap year, this was not.
Yeah, I see it. Just thinking about it.
Leap year is divisible by 4, but divisible by 4 does not mean leap year.
Got it. Thank you.
Any other questions on the homework? Wow. All right. So then we'll stop the recording, and you have the rest of class to